in with you a little bit about friction. Now, tell me about this, because friction is not an unknown concept to you all. This is something that you've dealt with, and we've even talked about in this class. What do we mean by friction? Give me a raised hand. What do we mean? Yes. Okay, yeah, she's rubbing. Okay, yeah. Can you define it? Sir? Okay, two objects that are rubbing together, and as they're moving opposite of each other, this force that restricts that movement. I got you. What else? Okay, so the motion that's going, or the force that's being applied, it's going opposite of that. And that's how we've shown it consistently in our diagrams, right? That here's the force going up the slope, and friction is resisting that, going the opposite direction. I would agree with that. Where does friction come into your lives? Okay, all right, there can be. But that's more like normal force, right? They're just kind of holding it there. Okay, if you're moving it around, I like that. Okay, where else does friction come into your lives? Driving, absolutely. We'll talk more about that. Driving is a huge piece based on friction. You comfortable that that's the only force keeping you on the road? Is friction, right? The other thing that's allowing you to turn is friction. Well, we'll talk more about this. What else? How else? That's a big obvious one. Where else does friction play a part in your world? Walking, right? Think about trying to walk on ice and how difficult that is. It's because ice has a tiny coefficient of friction. There's very little, almost frictionless surface. So it makes it very difficult to walk. Okay, what else? Think. Sorry? A slide, sure, if you're on the playground, that's going to be the thing that kind of irritates your behind as you're going down. I like it. Or keep you from just flying off and catapulting and hurting yourself. Could be sliding if it wasn't a level surface. I agree. Yeah. Sure. Yeah. So this is kind of the force that's preventing things from just moving continuously. Right? Think about sports. Right? Playing soccer. Right? You kick that ball, it rolls in the grass. Does it just continue to roll infinitely? No, it slows down, right? So friction plays a huge role in a lot of the pieces that we do. Now, what you may not have known, and I certainly didn't know it until I started studying physics, that there are actually two types of friction. Somebody want to tell me what they are from your textbook? So we have kinetic, and we have, what's the last one? Static. Okay, so let's just define our words. What do we mean by kinetic friction? Like, what does kinetic mean? Kinetic energy, it has the same kind of root, absolutely. What does it mean, though? On moving objects. Okay? So the friction that's when something is actually moving is kinetic friction. So this is when something is moving. So what do we mean by static then? The opposite, right? It's when something is still. It's not moving. Let me ask you this with a raised hand. How many of you have ever pushed a car? Yeah? Something's broken down or someone's stuck in the mud. You're trying to push. We used to do, and I wish that we had this ability to do this. Maybe we'll have to do this for a lab here at some point. To push a bus. We used to do this as like one of the games that we played at Spiritual Retreat. That at Mount Etna there's this nice road that goes up from the dining hall to the cabins. That's at an incline. And we'd have a competition to see, could you push this bus, or who could do it the fastest? To push the bus, I'm sure. Yeah, those of you who have older siblings, I'm sure they did it. Are you comfortable? The hardest thing of getting that bus moving is not keeping it going. It's the initial start. Do you remember this from those of you who have pushed before? Or think of you trying to move like a heavy something, like a refrigerator or an entertainment center or your your dresser kind of thing. That initial push, that's the hard. Once you get it sliding, it's easier, right? Once you get the car rolling, it's easier. There's still friction happening, right? It's still trying to slow down. If you don't keep pushing, it will slow. But it's easier than that initial piece. And that's because static friction is greater than kinetic friction. It takes more force to get something moving than it does to keep it moving. Does that make sense? There's a formula that gives us friction. So the force of friction is equal to really only two letters that you have to know. The first you already know, it's the normal force. Right? So the force of friction is equal to the normal force multiplied by this thing that we call a mu. Mu, like what a cat does, but not meow. It's a mew. It's like a little kitten. Mew. Right? And again, this is a Greek letter that they've assigned. And this mu stands for, we call it the coefficient of friction. And the coefficients of friction, they vary based upon the surfaces that are involved. So in other words, the materials that you are interacting together, the things that are on top of each other that are moving, will determine this coefficient of friction. Can you give me something that you think would have a very high coefficient of friction? Like a lot of friction between these surfaces. Can you give me? Sorry? Rubber and what? What's it against? Okay, two pieces of rubber together? Sure. That would be a pretty high coefficient of friction. What do we normally put rubber on? On our wheels, which those are riding on the pavement, right? So asphalt or concrete, right? Those are good high friction, high coefficient of friction. What else? What about if I was to rub something on your face? What would be something you would not want me to rub against your skin? Sandpaper, high coefficient of friction, definitely. Anything else is coming to mind? What about your tennis shoes? Sure, that is rubber. Yep. That would, right? If you get those nice squeaky clean, like your brand new shoes, right? There's definitely some friction that's present there on purpose, right? Because they want to be able to stop and cut and move when they're playing basketball. Okay, how about things that would be very, very, very smooth, very, very little friction? Sorry? Water. There is some friction present there. Absolutely. A soft blanket, nice little fleecy blanket. Oh, that'd be nice. Yes. A dog. Okay, so like the fur. Absolutely. It's good. It's good. You see the difference, right? All right. So this mu, you would have to be given. I want to show you that in your textbook, there on page 132, they have a list of some of the coefficients of frictions of different items. So take a peek there if you would. Just one page over. I have to use my phone because I don't have my textbook here. It's in table 2. Sorry, your figure is... Yeah, table 2 on page 132. So they show you static friction and kinetic friction. And I'll show you the kind of the same thing up here, that this is just from Wikipedia, where you have static friction and kinetic friction, right? And they're giving you, here are different metals or different pieces. So if we want to take concrete on rubber, right? When it's dry, it's a 1.0. That's a huge amount of friction, right? This coefficient of friction is very high. But are you seeing that when it's wet, it drops to 0.3? Significant, 70% difference, right? When I'm driving in motion, I'm at a 0.6 to 0.85. But when it's wet, down to 0.45 to 0.75. And of course, this is more what we care about with rubber and concrete, because that's what we're driving, right? We're actually moving. So it's not the static friction we care about, it's the kinetic friction, right? But can you see that significantly lower kinetic versus static? For all of these pieces, oops, I'm writing and not moving. For all of these, the kinetic friction is less than the static is. So you don't have to memorize these by any means. And the problems you'll do, you'll be given this coefficient of friction, or you would find it. If they gave you the force of friction, because remember, here's our equation. It's not a complicated equation at all, right? If they give you the normal force, or of course you can find normal force, right? Because remind me, please, how do we find normal force? What's the equation for normal force? Your mass times gravity, the acceleration of gravity. Right? So if they give it to you as a mass, you assuming that this is happening on the planet Earth? Though there is, I will put this plug in. Today they're landing a rover on Mars. It's not, you can't really watch it in real time. You can get onto the JPL's website and you can like live stream in mission control, but it's not like you can actually watch it. Does that make sense? I thought about putting it up there, but then when I found out that's all it was just a bunch of people sitting at computers talking. Landing today. Years ago. Yeah. Yeah, it's a decent way to get there. Maybe not a year, maybe a year ago. Depends on where we are in how close Mars and the Earth are. I don't know exactly when they launched it, but about a year probably. It all depends on where the Mars and Earth are, and they usually will launch it when they're closest together. Yeah. But yeah, worth checking out. Are you with me, my friends? Force of friction is this coefficient of friction multiplied by the normal force. And are you comfortable that they will use force of friction kinetic, and therefore you'd have the K there? Or they would use force of friction static, and so you'd have the static mu? So just don't be confused. They love to put little subscripts on physics stuff. That's all that's meaning. Sir? Well, you could. That's what I'm saying. If they gave you the force of friction and they gave you the normal force or the mass, then sure, you could solve that for mu. Definitely. It'd be the same thing. Should we try one? All right, let's do it. So there in example problem number 3, that's there on page 133, it tells you that you push a 25.0 kilogram wooden box across a wooden floor at a constant speed of 1.0 meters per second. The coefficient of friction is 0.20. They want to know how large is the force that you exert on the box. Are you with me? So let's make a little force diagram here so we can see what's happening. Here's our box. And it's nice, they actually made it a box. I don't have to just draw a box to represent the thing. What forces are acting? Gravity, cool. Gravity is going what way? Downward, of course. So that's our force of gravity. Is there any force opposing gravity? The normal force, good. And you're comfortable that should be equal and opposite, right? Okay, what else? It's always going to be gravity. It's correct. Yep, that's where normal force comes from, right? It's that force from the perpendicular surface that opposes gravity. Okay, what other forces are happening here? Sorry? Okay, cool. So the person's pushing. Can we have him push that way? And what's opposing that? The force of friction. So are you comfortable that if we can calculate what that force of friction is, that's how much you have to push, right, to overcome that?
So just for like
You're correct. You're correct. Now, what they're going to have you do is they're going to have you calculate, and they'll say these two are equal, right? Because you are overcoming. But you're right. You need to push a little bit more than the force of friction to get it to go. Does that make sense? But they basically see them as being equal to calculate the amount. You with me? All right. So yes, if you would put your answer as more than that number, I'm fine with that. No problem at all. Okay, sir. Well, this is a question that we'll come to. For what we're doing right now, it doesn't. What does it tell you, though, when we say that we're pushing it at 1.0 meters per second? I can't hear you, sorry. Okay, so we don't need the meters per second to find normal force, right? We just use mass and we use gravity. So the 1.0 as a number doesn't really affect our calculations at all right here. But what does it tell us? There's some sort of movement, right? There's some sort of velocity. So would this be static friction or would this be kinetic friction? Does that make sense? They're telling us that this box is moving. So therefore we have to use the kinetic friction between these two guys. Now, they gave you the mu, right? This is our mu, 0.20. So it's not like we have to look up on a chart. But if they would have told you that this is a wood box sliding across concrete, well, you could look that up. We could actually go to a chart like this and find, here's wood on concrete, here's my static mu is 0.62. They don't give us a kinetic. I wish they would have, but they didn't. So we would know which one to use based upon the fact that it's moving. Does that make sense, my friends? No, same equation. Right, right. So you would know which mu to use, whether it's moving or whether it's not. Oh, good. Are you with me, friends? I'm saying this number is different whether it's static or kinetic. Right, if it's given to you, you don't have to worry about it. Well, you could label it just to be correct. Sure. Yeah. But I'm saying if they had not actually given this to you, Michael, then you would know based upon this you would have to use the kinetic friction mu because it's moving.
So if it was 0.0 meters per second, that's the only time you
Right. Or they're asking you how much do I have to push to get it started? Or then how much do I push to keep it going? Right? Kinetic versus static.
If they didn't give us the mu, and we do it with kinetic or static, how would we?
You could use the chart that's in your textbook. You could look it up online. Between the two pieces, between the two materials.
What about tests or something?
I would give it to you, or I'd give you a chart. Mm-hmm. Yeah. All right. So, what's our equation that we're trying to use here to solve this guy? Force of friction equals our mu times the normal force. And I can replace the normal force with umg, right? Sir?
Because you said you could find mu, just use that
Uh-huh. Mm-hmm.
So then if it doesn't tell us, if it does tell us if it's static or
Mm-hmm.
but they would give us the same answer.
It would depend. I mean, you'd have to go up with the problem they're giving it to you. In other words, are they describing conditions when it's moving or when it's still?
No, yeah, no, but you said that static and kinetic are different answers, but
The force would change. This force number would be different if it was kinetic versus static. It would take more force of friction here to get something moving than it does to keep it moving. Does that make sense? Yeah, I see where you're going there. This number would be different if you were trying to solve for mu. They would. The problem would give you that information, certainly. All right, can I plug in numbers here, guys? What do I plug in for mu? Oh, we don't, because we already know it. Do we know normal force? But do we have any forces listed up here? That's not the force, that's the acceleration. Yeah, so no, we have to calculate it, right? So 0.2 times my mass of 25. Do I have to change this 25? Or am I good with 25? How do I know, guys? It's kilograms. Kilograms, if it was grams, you'd have to make it into kilograms. And then times 9.8. So when I pop all those guys together, and again, you can see it on your work in your textbook, that comes out to 49 newtons. What's that? Sure, they give you a direction, even though they don't really give us any sort of.
So you don't.
Well, because this is moving, we know it's what? Yeah, we know that this was the kinetic friction that we found, right? So therefore, we know that if Nick is the one actually pushing this box, he has to exert just more than 49 newtons of force to keep this box moving. Yeah, I got you. Or greater than. They don't, but I hear what you're saying. I hear what you're saying. Does this make sense, my friends? What I want to make sure you understand, there's nothing new here, equation-wise, other than just simply we're adding this coefficient of friction to it. You already know normal force. You already know that that's mass times gravitational acceleration to get the force of gravity. Because, of course, like we showed here, the force of gravity is equal to the normal force. Are we cool? Okay, so what I am looking for you to do, please, in this last bit of time we've got left, it is the 5.2, oh my, excuse me, 5.2 problems, and it is 18 to 21. I would love for us to spend, we've got about 15 minutes here, let's spend some time working there.